Oh, and welcome to 9 of our lecture series. So this week's lecture is going to be about momentum and conservation of momentum. Now, what is momentum? It's pretty easy to define that momentum P is equal to mass times velocity. So momentum mass velocity. So this is going to end up being a conserved quantity like energy. The difference being that unlike energy, which is a scalar value and only tells us the magnitude of the velocity, this is also going to tell us the direction of the velocity because it's a vector quantity. So this is a good tool to use in conjunction with conservation of energy in order to find the dynamics of the system. So that's all well and good, but first we're going to define another quantity, dj, where j is called the impulse, is equal to f dt. So this is related to force, and instead of integrating over position like we did for work, we're going to integrate over time like we did for, or like we haven't done yet, but in a similar way than we did for work, except for instead of position, we're talking about time. So impulse is equal to f, the integral of f dt. And if we remember something about that you learned in calculus, you'll remember that F average is equal to 1 over delta t, the integral of F dt. So it's equal to the integral over time or space or whatever you're averaging over, divided by the total time that is integrating. So from this, we get that J delta t is equal to F average. So this is a kind of useful, uh, yeah, this is a pretty useful answer as, and then J and F are both vector quantities, of course. So this is a pretty useful answer as it tells us that we don't need to know the force going on at all given times. We only need to know the average force in order to calculate the impulse. And then the other thing that we're going to uh, find out from this is how this impulse relates to momentum. So we have J is equal to F delta T, or dt, is equal to M A dt is equal to M dV, and let's just bring the M out ahead in front of this, dV dt dt. So this is kind of the fundamental theorem of calculus. Um it's a version of the fundamental theorem of calculus where if you take a derivative of some function and integrate that function, then you're just going to find the original function that you had before evaluated from your point A to point B. So this is equal to M times V final minus V initial equals M delta V. So as we can see, this is equal to the change of mass times delta V. So if mass doesn't change either, then this is going to be equal to delta mv, which is going to be equal to the change in momentum. So from this, we are able to recover to relate momentum to our forces and to our impulses. So this is called the impulse momentum theory. And then while we're at it, because uh J equals delta equals F average over delta T, then this goes to delta MV equals F average, delta F average over delta T, which goes to dV dF dt as we take delta T and delta F average to their infinitesimal uh values. So MV, oh, sorry, I got that wrong, completely wrong. That was a really big mistake. J delta T equals F average so J delta P delta T equals F average. No, that's also not going to lead us to the right position. So basically we got that J equals dF dt equals delta F delta T for large values, but we're just going to ignore that because I don't know why the book bothered to bring in delta F delta T. Or D. Wow. Wow, I am just completely loving this because I know that it needs to end up in the opposite direction. dJ dt is equal to F is equal to dF. So dP dt is also equal to F as dJ is equal to dP. So F is equal to the change in momentum over time, the same way that F is equal to the change in um yeah, the change in potential energy over space, or negative the change in potential energy over space. So that is uh pretty simple so far. Momentum isn't all that crazy, but I'm going to go on about conservation of momentum, which is also not that ridiculous of a concept. So remember that F equals dp dt. And we also know that F of 1 on 2 or 2 on 1 is equal to negative F of 1 on 2 by Newton's third law, which states that every reaction has an equal and opposite reaction. So dp dt, the change in momentum caused by 2 on 1 is equal to the negative change in momentum caused by 1 on 2. So dp21 dt plus dp12 dt is equal to 0, which means that dt of p21 plus p12 is equal to 0, which means that p21 plus p12 is constant. Which is just conservation of momentum. It means that this value, this vector value, is always going to be the same value no matter what you do to it, no matter what forces are acting on it, as long as you keep the entire forces in the system. So as long as your system has all of the forces in it and all of the interactions within it, if you're looking at the total universe, then this P21 plus P12 is going to be constant. That means that there's always going to be no change in momentum over the course of any interactions that you're having. And then we can, of course, uh, uh, ra we can, of course, make this less specific to just P1 and P2 and say that Pj from 1 j equals 1 to j equals n equals P1 plus P2 plus dot 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 Pn is also constant by the same values if you have multiple forces acting on each other and multiple objects in your system, then the value of the momentum is always going to be constant. So that is the main takeaway from today's lecture, that just momentum is constant. Now, how do we use this value, or how do we use this? So let's do the three types of collisions. Um, three types of collisions and see how conservation of momentum relates to these three types of collisions and how conservation of energy relates to them. So we have three types of collisions: explosions, where you have more kinetic energy after collision; inelastic collisions, where you have less kinetic energy after the collisions. And elastic collisions, where you have the same amount of kinetic energy after the collision. So for an explosion, what you might see is that you might see one mass breaking up into multiple masses. And then these masses aren't to scale because I'm realizing that I'm making them about as big as the initial mass itself. But when you have an explosion, it's going to have more kinetic energy because you can have it with initially zero kinetic energy. So if explosion initially has zero kinetic, then when it explodes, it has to have more kinetic energy because the energy is being because the energy is being taken from other forms of potential energy or heat, uh, but has the same momentum. The same total momentum, where here we have P1 plus P2 plus P3 plus P4 equals 0. So M times V1, M1 V1 plus M2 V2 plus M3 V3 plus M4 V4 equals 0, which means that they have to be going in some sort of opposite directions. They have to be going in different directions so that these vectors, these velocity vectors, and these momentum vectors have to be able to, the velocity vectors don't have to cancel out, but they need to be pointing in different directions in order for the momentum vectors must to cancel out. And then you can also have it so that if, say, you're talking about a firework which has an initial velocity, then all of the PJs, all of the individual momentum from j equals 1 to j equals n equals the original velocity, the original mass times the original velocity. So all of the momentums are going to add up to the original velocities. So this isn't a case that you're going to see very often, but it is an interesting case where the momentum vectors, where when there's an explosion, and of course you see this very often in real life that there are explosions, you see um, dynamite or fireworks or something like that. But in physics classrooms, this is probably the least seen uh type of collision because it's also the most likely to go awry and also the most likely to be difficult to keep track of. So this is explosions. Uh, an inelastic collision is just a collision where the particles, the objects moving lose kinetic energy, but they still gain, they still have the same, they lose kinetic energy, but they still have the same momentum. So for uh this to occur, it's just basically the energy instead of being used to move it might be used to like cause chemical bonds or be released or being released as heat or sound after the collision. And then you also have a perfectly inelastic collision, elastic collision, where both bodies stick together after the collision. And then this is the lowest potential energy you can, the lowest kinetic energy you can get to. So, for example, let's draw a perfectly M1, V1, M2, V2, collide, and they go to some mass M1 plus M2 times V final. So they start with individual momentums and then they end up with the same momentum after the collision, but they have a different kinetic energy. So just a second. This is a really simple calculation, but I'm seeing if they have in the book the oh no. So they don't have equations for the kinetic energy, but we can find those equations if we want to. So I think I'm going to do that just because I'm already up here talking, so might as well. So M1 V1 plus M2 V2 is equal to M1 plus M2 V final. So V final is equal to M1 V1 plus M2 V2 over M1 plus M2. So if this is the case, if V1 is pointing in the opposite direction as V2, then it's going to have less kinetic or less V final than the uh Yeah, it's going to have less v final than the if they're both pointing in the same direction. And then one can be pointing in the opposite direction of the other, uh, and be going significantly faster. But if the mass of the second object compared to the first object is significantly larger, then it can still end up going in the same direction as the second object, even though uh, it was going in the velocity of one object was much greater. So this is conservation of momentum, not conservation of velocity. So change the velocity changes, and that depends on how much mass times velocity uh you initially had, rather than just how much velocity you initially had. So v final equals m1 v1 plus m2 v2 over m1 plus v2 m1 plus m2. So I'm still working with vectors right now because this is a vector quantity, but this is where it gets a little difficult. M1 v final squared is equal to 1/2. Oh, sorry, not M1 v final squared. M1, 1/2 M1 plus M2 v final squared is equal to 1/2 M1 plus M2 times v final dot v final, because v final dot v final is equal to v final x squared plus v final y squared plus v final z squared, because it's v final x dot v times v final x plus v final y plus times v final y plus v final z times v final z. And if you're not convinced of this, then you should go over the values of dot products again, or the properties of dot products again, which is equal to v final squared. So 1/2 m1 plus m2 v final dot v final is equal to 1/2 m1 plus m2 times m1 v1 dot m1 v1 plus 2 m1 m2 v1 dot v2 plus m1 m2 v2 dot m2 v2 plus all divided by m1 plus m2 squared. And then this is equal to 1/2 m1 squared v1 squared plus m2 squared v2 squared plus 2 M1 M2 V1 dot V2 over M1 plus M2 is equal to 1/2 is equal to the kinetic energy 1 times M1 over M1 plus M2 plus the kinetic energy from initial of 2 times M2 over M1 plus M2 plus 2 M1 M2 V1 dot V2 over M1 plus M2. And it may not be immediately obvious, but this is going to be less than the less than or equal to, or probably less than, I don't think that it can ever be equal to K1 plus K2, which you can see definitely in the K1 times M1 over M1 plus M2 values. Because M1 divided by M1 plus M2 is going to be less than 1, so it's going to be some value less than 1 times the initial kinetic energy plus some of 1 plus some value less than 1 times the initial kinetic energy of 2. The only sticking point is going to be the 2 M1 M2 times V1 plus dot V2 over M1 plus M2. But yeah, but that's going to end up being yeah, that's going to end up being less than the value that needs to overtake this to overtake this K1 plus K2 value. So what we need to prove, and I'll see if I can do it off the top of my head, is that 2 M1 M2 V1 uh yeah, so that's the main thing that needs to be proved. I'm just going to spend no. Uh okay. Yeah, so I'm going to try proving that right now, just because I've already taken U so far. So K1 M1 over M1 plus M2 is equal to K1 minus M2 over M1 plus M2. And then K2, same thing for K2 M2 over M1 plus M2 is going to be equal to K2 is equal to K2 minus M1 over M2. So delta K is equal to K1 plus K2 K1, K2. M1, M2 times M1 over plus M2 times K2 minus, or it's going to be K1 minus M2 over M1 plus M2 K1 plus K2 minus M1 M2 plus M1 K2 is equal minus plus 2 M1 M2 V1 dot V2 over M1 plus M2 minus K1 minus K2. So delta K is equal to negative M2 over M1 plus M2 K1 minus M1 over M1 plus M2 K2 plus 2 M1 V1 dot V2 over M1 plus M2. So V1 dot V2 V2 is less than or equal to V1 times V2, the magnitude of V1 times V2. So which is equal to square root of K1 divided by times 2 divided by M1 times square root of K2 times 2 divided by M2. 1/2 M2 squared equals, which is equal to 2 square root of K1 divided by M1 M2. So delta K is less than or equal to four yeah, I forgot an M2 there. 4 M1 M2. So 4 times K1 K2 M1 M2 divided by M1 plus M2 minus M2 K1 over M1 plus M2 minus M1 plus M2 divided by M1 plus M2 K2. Which is equal to negative uh, M2 minus M1 M2 K1 minus M1 K2 squared over M1 plus M2 is plus 2 square root of K1 K2 over M1 plus M2 over M1 plus M2. Yeah, and then this this is less than this. So delta K is less than or equal to some negative number. So delta K equals negative. And then the way that we can tell that this one is less than this is because this is a factor in K1 M2 minus M1 K2. So that's going to be equal to K1 M2 minus, and then it's the square root of these. So that's going to be equal to K1 M2 plus K1 M2 minus 2 square root of K1 M2, which is going to mean that this value over here is going to be greater than this value over here because 2 K1 plus K2 M1 plus M2 is going M1 times M2 is going to just be one of the factors in this value that's going to be less than uh less than the total squared. If that makes sense, hopefully it does, but this is just the proof that I came up with off the top of my head. I really wasn't planning on doing this, but I ran my mouth off and it ended up being necessary, basically. But delta K equals negative. So therefore, this value is going to be positive. Or this value is delta K is going to be negative, therefore this value is going to be greater, is also this change in energy is going to be less than the initial energy that you had. So uh that's good. I'm kind of surprised I was able to do that. I can't edit these videos, so I can't just edit that out, so I apologize to you. But that's going to be the case. And then the last uh collision that we're going to come across is an elastic collision. So for example, one example of an elastic collision uh is where you have one ball moving with v initial. It hits another ball that's stationary, and then this goes to uh, m2 v2 plus, or yeah, sorry, m1 v1 and then m2 v2. So basically, if m1 is equal to m2, then this becomes really easy, but let's just say that m1 v initial is equal to m1 v1 plus m2 v2. Then in an elastic collision, 1/2 m1 v initial squared is equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared. So I'm not going to, I already wasted enough of your time going through that proof with proof about inelastic collisions. So I'm just perfectly inelastic collisions. So I'm just going to say that these are the conditions for elastic collisions. And then come up with the answer for M1 equals M2. So if M1 V1 equals M1, or V initial equals M1 V1, which is V final, plus M2 V2. And then M1 is equal to M1 equals M2 equals M. Then M V initial equals M V final V1 plus M V2. So V initial equals V final or V1 plus V2. And then 1/2 M V1 squared, V initial squared is equal to 1/2 M V1 squared plus 1/2 M V2 squared. So V initial squared is equal to V1 squared plus V2 squared. So the only case where this can happen is if one of these V1 or V2 equals 0 and the other one equals V1, V initial. So in this experiment, in this setup, it has to be V2, which is going to follow through with the follow through with the it has to be V2 that's going to follow through with the whatchamacallit, with the momentum, because V1 can't keep going, because if V1 keeps going, then it would just pass through V2. So if you V1 runs into V2, then V2 has to keep going because V2 doesn't have anything in front of it, but V1 has mass 1 has mass 2 in front of it, so it can't keep going. So V2 has to be the one that goes forward, and it transfers all of its energy, all of its momentum into the second one. So if you've seen a billiard ball, you've seen this happen. If you've seen something called Newton's cradle, which is those uh, balls hanging from ropes that one of them is pulled up, it puts all of the momentum, all of the energy through the balls in the middle, and then pushes the other one out. So that's called a Newton's cradle. So something like this is called Newton's cradle. So if that's the case, then that is just going to transfer all the energy, all the potential into the next ball, or not all the energy, all the momentum into the next ball, and not care about anything else. And lose all the or not care about anything else. It would lose all the values for earlier for the mass 1. It would lose all the energy and all the momentum. So those are our 3 types of collisions. Last thing I'm going to do before I move on to the next section is just going to be an example of a car with some velocity greater than a truck uh, ramming into each other for a perfectly inelastic collision, and uh, seeing what happens. So V car, V truck, M car, V car, M car, M truck. So I have been using vectors this entire time instead of just talking about one-dimensional analysis, but all the examples that I've done so far have been one-dimensional. But let's just be a little clearer that P1 plus P2 is equal to M1 V1 plus M2 V2, and that these are vectors quantities, and then these vectors are conserved. So that's something that I've already said, so I'm not even going to bother writing it out, but uh, the main thing is that F equals dP dt yields Fx equals dpx dt, Fy equals dpy dt, Fz equals dpz dt. So that's the main thing that you're going to get out of talking about vectors that we haven't already talked about. But we talked about V final for a totally inelastic collision being equal to M1 V1 plus, or in this case, M truck V truck plus M car V car over M truck plus V truck. Or M truck plus, sorry, M car. I'm going to take a break pretty soon, so hopefully that will take care of my verbal flubs. So in this case, V final is going to be M truck over M truck plus MC times V truck I or V truck J plus MC. Actually, let's clean this up a little bit. It's going to be equal to 1 over MT plus MC VC I plus MT VT J. So if we set MT so yeah, this is pretty simple. This is just going to give us all of that. I was going to plug in some numbers, but I realized that we don't need to. So V final squared, V final, the value of V final is going to be equal to the magnitude of V final is going to be equal to 1 over MT plus MC square root of MC VC squared plus MT VT squared. And the angle that it makes with the x-axis is going to be equal to MT, arctangent of MT VT over MC VC. So that's just basically a problem that you're going to be able to solve for if you just plug in your values. So this is a perpendicular problem where both vectors are perpendicular to each other, but you can do this for any type of vector that you see. All right, I'm going to take a few minutes of break, so I'm going to stop recording now. And then just be aware that there are going to be more questions or more there's going to be more lecture in the further tabs of this lecture notes, or in these lecture notes of this Zoom recording. All right, see you in a bit.